Have you ever driven between the two cities, listening to some radio station, and suddenly at some point, started hearing more than one stations? The reason is that both stations had the same carrier frequency. This is a case of interference. To avoid interference, not everyone can use any electromagnetic wave of any frequency one likes. We live in a frequency division multiplexing world. Electromagnetic waves of different frequencies, from the low megahertz range for AM radio, to the tens of gigahertz range for high-frequency 5G, are regulated and allocated. Different communication signals are allocated to different frequency bands, from very coarse to very dense division. Wi-Fi frequency is a coarse band around 2.4 or 5 GHz. AM radio frequency is a very finely divided band with only 10 kHz separation between the channels. In the previous step, we use a high-pass frequency filter that selects signals with high-frequency carrier, but will that works if the interference is not low-frequency noise, but other communication channels with high-frequency carrier also? We can demonstrate that next. As evidenced, the low-pass filter in this case cannot block out the interference like it does for low-frequency noises, which was demonstrated in the previous video. The problem here is that the interference signal also has a carrier with a frequency that is in the pass-through band of the filter. Fortunately, its carrier oscillates at a different frequency than the one of our signal. If two radio stations have different frequencies, which are the station numbers, they can be distinguished by tuning the radio to the frequency of interest. Here, our signal carrier frequency is 9 kHz, while that of the interference is 40 kHz. We can use another circuit that allows 9 kHz passing through, while rejecting 40 kHz. This is the next circuit to be studied, a low-pass filter. That, given a complex signal, this circuit, on the rightmost of the photograph, will take the signal and interference input directly from the adder circuit that is not shown. We need not be concerned with details of the circuit at this point. It is sufficient to say that, given a complex signal, the circuit selects the portions of the signal that have low frequency oscillation, and greatly attenuates those that oscillates at high frequency, which is the interference in this case. It appears quite similar to the low-pass filter to the left. Indeed, it is just a swap of positions between the resistors and capacitors. The values of the components, however, are necessarily different for the designed frequency range. If you have not learned Laplace transformed circuit theory, there is no need to be concerned with the details. It is sufficient to summarize that in circuit theory, it is a second-order circuit that filters low frequency as shown in the Bode plots, both from calculation, and from experimental measurement as shown. Next, let's look at its output, given the signal and interference input. It is evidence that the very low frequency remnants of the interference is further reduced by the low-pass filter. When both filters are serially connected together, they form a bandpass filter, which rejects both low frequency and high frequency, and ideally, should allow only the signal portions that are in a narrow band around the desired frequency. This lab, however, is not intended for narrowband filter, because it is designed for the concept of wide band pass filter. It is evidence that the interference with 40 kHz carrier is heavily attenuated compared to the intended message signal by the low-pass filter. But one can also see the remnants of the interference, although quite small compared to the wanted signal. This is similar to the remaining spikes that are evidenced in the video on the high-pass filter, as no filter is perfect. It is clear that each filter, high-pass and low-pass, has its own specific use, and both are needed. This is what will be considered next. Now, both filters will be used. The signal and interference will pass through the high-pass filter. The output will subsequently pass through the low-pass filter. One can observe the output of the joint filter. It is evidence that the very low frequency remnants of the interference is further reduced by the low-pass filter. When both filters are serially connected together, they form a bandpass filter, which rejects both low frequency and high frequency, and ideally, should allow only the signal portions that are in a narrow band around the desired frequency. This lab, however, is not intended for narrowband filter, because it is designed for the concept of wide band pass filter. Again, as shown, both calculation and experimental measurements agree quite well on the bandpass property of the filter, which is now treated as a single unit, a bandpass filter that consists both circuits. One may wonder, why is there a need for wideband filters? There are many reasons. The manner that the frequency spectrum is utilized is quite complex. A simplest answer is that there are several levels of granularity in the division of frequency, from very coarse with wide bands, such as several GHz, to very fine with ultra-narrow band like 10 kHz. Hence, there are a multitude of bandpass filter types for the wide varieties of applications. Here is an example of a wide bandpass filter that many cannot live without. It is the ubiquitous Wi-Fi filter that come in all forms, shapes, and properties. In this Lab 6, the objective is to show how circuits, in this case, second-order types that you learn in circuit theory, can be designed for filter applications. In fact, although for the audio frequency range below 100 kHz, all signal processing is now practically digital, it should be remembered that analog filters like these were the pioneers in applications such as the audio equalizer. In fact, some low-cost audio components still use some of these analog circuits. Back to our filtered signal. The bandpass filter has done its function, removing the interference with higher frequency modulation, as well as the low-frequency remnants of the interference, which act like low-frequency noise. As mentioned in another video, carrier is like a vehicle. After the passengers are transported, the passengers must get off the carrier. The high-frequency modulation of the message signal is no longer needed. There is a last circuit of this lab that does demodulation, which, as mentioned in another video, can also reduce the magnitude of the remaining spikes. That will be the next topic.